Testing. Testing. Okay. Good morning to everyone. Hope everyone wake up. If not, let's do a little bit of warm up on what we did on Wednesday. So let's recall the idea of a limit of a function. It's the definition of a limit. Okay, so the idea of a limit is we want to see how close, we want to see what's the value of fx approach, okay, when it is near some neighborhood x. Okay, let's call this a, when x equals to a. Let's say we define a piecewise function here. At a, maybe we define it as a k instead of this L. Okay. So the point here is, let me draw a bit longer. Okay, so if you look around the L, okay, if you look around the neighborhood of L, okay, let's say there's some length here, okay, call it epsilon. Okay, and then you can read on the region of your function. Okay, then you will see that around A, okay, there are points that are close to L. So if we're gonna write a limit of x to A of let's say this is our fx now. Okay, how about this one? We change it to y6. If we write limit of x to A of fx equals to L, is when no matter how close, okay, no matter how close to L, okay, you still find these fx close to L. Okay, no matter how close. Okay, you can pick even smaller region. Okay, if you pick even smaller region, okay, you pick smaller region, you will still find fx close to L. Okay, does it make sense? Okay, this is not true. For example, this is not true for this k here. Okay, if I move this k up a little bit more, maybe a bit even more, so that we can differentiate between k and L. Okay, this is not true for k. Obviously, if you pick a very large region, like let's say this big, okay, well, this, if it is this big, obviously you can find that there are points close to k, but this is not true for any region you fix anymore, right? Because let's say you fix very close region around k, so let's say we fix this region here, and you cannot see your function anymore. So we wouldn't say that. So we wouldn't say that the limit of fx when x approach a is equals to k. Okay, because if you get very close to k, okay, you cannot see your function anymore. Can you see any function? No, right? You are missing it. Okay. So if you want to say that the limit of f(x) is equal to L, no matter how small around L, right? Okay, you should be able to see part of so this is the idea. This is the idea what on Wednesday we want to show you using the table. Remember the table? How you see the value approximate on the right, on the left. Okay, so this is exactly the same on the right, on the left. Okay, if you look at the small region around here, from the right, from the left, nothing. Okay, so this is the idea. Please keep this idea when you do the question. Okay, please keep this idea when you do the question. Okay, any question from last lecture? Any question? You try out the question homework. Okay, so we'll go through together now. Okay, let's go through together. Fine. Let's keep it. Okay, let's quickly discuss. Okay, I think before that, right, I should recall the limit law for you. So still remember this limit law here. Okay, so there are about 9 rules. Actually, most of them can be combined, but we separate it for the sake of understanding. So the important key of a limit law is you need to start with a function that has limit at a certain point, let's say a here. Then you can evaluate, okay, what's the limit of that function multiplying a constant, for instance. Okay, it's just equivalent to pulling out the constant. Okay, and if you evaluate a limit on sum of function, okay, you can split up the sum. Okay, you can calculate the individual limit and then add them together, right? Okay, similarly for subtraction, okay, the difference and then products of function also. Okay, you can compute the individual limit and then take the product. Okay. Otherwise, what you need to do here, you need to compute what is f(x)(gx) first, and then you look at the graph, what is the limit. Okay, then that will be troublesome. You need to compute the new function. But the point here is no need to compute the product. Okay, just based on what you know about the limit of the individual function is enough. Okay, but obviously you need to make sure the limit exists first. Okay, and then similarly for quotient, one extra thing you need to take care is the limit of the quotient cannot be 0. Okay, otherwise you are dividing by 0, which is undefined. Okay, 6, 7, 8, 9 is very convenient. Okay, it tells you exactly why you can do substitution of polynomials. So for 6, if you have a constant function, right, obviously the limit of a constant function is just a constant number. So this 2c is different. Please bear in mind. Anything beside limit must be the function. It's not a number. So how do you see a number as a function? Well, you just evaluate at every x, you get the same. Okay or not? Does it make sense? Maybe I write it here. So this c here is really a cx equals to c, like that. Okay? For every point, you evaluate to c. Okay, what's the graph of a constant function here? Let me test you. What's the graph of a constant function? Think of like y equals to 2, y equals to 1. What's the graph? Any idea? Y equals to 1, y equals to 2. Right? Straight line, not enough. It's a horizontal line. Because vertical line is also a straight line, right? Linear line is also a straight line. Okay, so it's a horizontal line. Okay, where cx equals to x actually is the horizontal line. Okay. So for 7, 7 is also a straight line. Okay, it's a linear line in particular. Okay, linear line. So what's that? What's the graph of that linear line? Okay, it consists of all points such that x equals to a, y also equal to a. And so you go from left, go from right, go from right. Towards x equal to a, it must be also y must be also going to a. Okay, no. Should I draw it? How about I draw it? So y equals to x looks like this. Okay, and then here 0, 0. Okay, and for the rest of the point, for example, this could be 1, 1, and then 2, 2, right? Okay, so let's say we plot another more, one more, 3. How about here? So I put a 3 here. Okay, so let's say if I want to consider x to 2 of x, okay, so you should go from right and left of 2, okay, and then see where this point approach to, and it is 2. Okay, so this is 2. Okay or not? Okay. Similarly for 8, if you want to consider the limit of more products, okay, it's just multiplying the product of limit. And 9, you can see that the square root actually what we call as a commute with limit operation here. Okay, so meaning when I say commute, right, meaning you can bring the square root outside. Okay, you can bring, in other words, you can bring the limit operation inside. Then you can bring this thing. Okay, and then 1, 2, 3 property of 1, 2, 3 is what we call about linearity. The linearity. And actually, limit is a linear transformation. Okay, so this is actually a linear transformation between the space of function and real number in particular. So these two are vector space. Have you guys touched vector space yet? Sorry, vector space in linear algebra. Maybe not yet. In Rn. No? Okay. Maybe we'll see a vector space in chapter 4 or something like that. Okay. Right. So look at this 2.13 here. So what's the thing you could do here? Okay, so they are products, right? They are difference. Okay, so we can use the linearity of limit, okay, to split it up. In particular, we know that the limit of the function x exists, okay, when s go to 4, okay, which is the usual, the basic linear function. So that's why we can split everything out. Okay, so let's use limit law. Okay, as we know that the basic function x is going to 4 when x approaching 4. Okay, so we can split them up. So what's the first thing I can split? I can split the difference. Okay. Next. So the limit law straight away split the difference. Okay, good. So I pull the negative out already. Then I can pull the scalar out, okay, because it's linear. And then the first guy evaluate on products, right? Okay, so you get the limit product squared. It's a 4 square. The other one you just get 2 times 4. So all together you get 4D. Is it? Check. Okay, good. Okay. All right. Any question for this one? Feel free to ask because in particular you guys are in first year, right? Your background could be all different because you come from a different educational background. It could be easier for some of the educational background, right? For example, maybe for the China one is easier. But you have to how to say, arrange your time properly. Okay. Um, more discipline yourself, because your course will only get harder. This is for sure. Okay, year one, year two, year three, then you will think that, oh, I don't have enough basic. So this is the time to build your basic. Okay, you need to do a lot of exercise, uh, do revision, make notes. Okay, I give you my recording, right? Okay, so if you don't have enough, I mean, like, you don't understand after this class, go back and rewatch the recording. Okay, and then did I record? Yeah, okay. So you go back and arrange your own time. You can watch at night, watch in the evening, watch during lunch or dinner, up to you. This is your plan, right? So, and then you have more flexibility, okay, to do your revisions. Okay, so self-learning is very important, because when you go to year two, year three, or university here, there's no one like um, give you every week homework you need to pass out or something like that. So you need to learn by yourself. Okay, no? So try and learn by yourself. And in particular, a lot of you are international students, right? I mean, China are also international students. Do you feel home here, actually, for the Chinese student? Maybe. Maybe inside university, maybe outside, then you'll be like, there's a language barrier. But I think you should appreciate this, okay? Mm, and I use this advantage, actually, okay, to help you to familiarize the environment here. Okay or not? Okay, this is pretty important, actually. Once you familiarize here, only then you can unleash your potential. Okay, it's natural that in first year you will feel homesick. Do you feel homesick now? No. Wow, you like to leave your home, is it? Okay, so it's usual to feel homesick. Even, I mean, like, when I was starting my university, right, people will say like, oh, your mood or your feeling is like a roller coaster. You feel like a roller coaster now. You get happy sometimes, then you get emo. Then you get happy, you get emo, get happy, get emo, get happy. Okay, but this is everything of this is very natural, I would say. Okay, so you need to grow up, right? You need to grow up. Okay, this is part of your life. All right, let's continue first. How about 2.15? Yeah, I told you what's the limit of f and g at x as 3 at 3. Okay, when x approach to 3. But I didn't tell you what is f and g. Does it matter or not? Does it matter? Does it matter if I don't tell you what is f and g? Matter or not? Huh? Depends, right? Depends on what the question was. Okay, the question is just ask about limit. It doesn't require you to like do any substitution to get the limit, right? We just need to use law. Okay, we just need to use law. So in particular here, since you know that the limit of f and g, but you are trying to figure out this new function here. This new function, how to build this new function? Is literally by products, by squares, by roots. Okay, so since you know what's the limit of the basic function, then you can use the what law? What's that law? What's the name of the law? And like you, what law will you use to find the limit? No need 1, 2, 3. In general, what's the name of those laws? Yeah, what's the name of that law? You see, that name is very important. It's not enough to just do question. Okay, you need to communicate with people now. Okay, you are in the university level. It's not like your Gao or what. You just do. People give you 100 mark, you 100. University, you need to communicate with friends. So to communicate, right, I should know your name. Okay, like students, what's your name? Jiapan. Okay, like Jiapan. What law should we use here? What's the like the big name for all these law, the 9 law there? Huh? What's the name? Good limit law. That's really only one thing you learn here, okay? So you must remember all these limits law, okay? So using these limit law, and we know the existence of the limit of f and g. Okay, we know the existence of f and g. Sorry, existence of the limit of f and g when x approach to 3. Then we can split out the product, square, and square root to compute the limit. Okay, so what's the first thing you could do here? Okay, first thing we should split out the what? Sorry, I hear something. Huh? Can you speak louder? f and gx? Not yet, because f and gx is somehow like too hidden. We need to split it up from outside. We need to split it out from outside. Right. So one obvious thing you can split up first. Huh? Okay. Actually, if you listen to what I said yesterday, our method is like working backward. Okay, our method is like working backward. So, okay. So should we do two type of step here? Maybe let's do two type of step here. Okay. So what's the number for product? Finding limit for product or function. So this is number 4. Okay. So by number 4, we know that limit of x to x of fx square is the square of limit of fx. Okay, so this is 4 square, which is 16. And then how about square root? Just now we say that the square, this is cube root. Cube root can commute with limit, which means that I can bring the limit operator into the cube root. Okay, so you can see why we set limit of gx is 8. Huh? Why? 8 is actually a cube of 2. Okay, so we make the calculation easier. So since we know the limit of these two, okay, we would know the limit of their products. So when I commute this square cube root, right, I'm using number 9. Okay. Lastly, we are using product again. Right, number 4. Limit of x to 3 of fx square times cube root of gx equals to what is this? So this is just splitting out the limit into products, which is 16 times 2. Okay. But oh, you were in the high school way, right? Maybe we just split like that. So let me write out another version of step. Let's see which one you prefer. Let's see which one you prefer. Then we can bring the limit in. On the other side, we can also bring the limit in using the same rule. Then the other one is square root 8. Okay, so altogether we get, sorry, this one too many root already. We get 16 times 2, which is 10. Okay, so let me explain what's the difference between these two. You can see that the two of them is the same. answer first of all. Second is they use similar step, but the order of presentation is kind of different. And the order of presentation is kind of different. So the green part here, we are using the limit law, okay, and then to build our new function. On the left-hand side, like we try to dissect this function here, okay? But why these dissection will work is because of the assumption. Okay, which left or right you prefer? Which working you prefer? Left or right? Maybe let's vote then. Can I see who like the red one? Okay, who like the green one? Very few. For those who don't vote, then you don't understand what I say. Huh? The red one. Yeah, the red one. Okay. So why do you like the red one? Shorter. Ah, shorter. Okay, okay. Why the left one is longer? A little bit more step. Do we have more step? Actually, it's the same step, right? Actually, it's the same. Huh? You prefer the right one. Okay. So the left one is more logical. Okay, it's on how we can use why we can write down the red one is basically the green one. Okay, so if you even if you don't write that, it's fine because this is not a MIT class. I mean MIT degree. But you need to know that the point you can write down the red one is because of the green side. Okay, this is the right logical step. Okay, why we can dissect them. You cannot just simply dissect them. I mean, all of us like to dissect things, but we need to like tell people why that. Otherwise, you are just messing around. You could easily get wrong answer in particular. Okay, you will easily get the wrong. That's why we want to know why it works. Otherwise, it'll be wrong. Okay, any question for this? I think for this class, we are quite happy if you can write the red one plus you know which limit law to write. Before number 9. But you don't need to remember. Okay. If you use it correctly, then we will know what you are using already. Okay. If you don't write it, any step, like for example, if you I have a student like that, if you like you don't write this now, you don't write this now, and then you write these two, then you will have no marks. I don't know how you compute the answer. So okay, the thing that told me was yeah, sure, sure, sure. Okay, no worries. Okay, so the reason they told me was I wrote in the draft paper. Ha. You write in the draft paper is gonna throw away. Who gonna check your draft paper? Okay, so make sure all your solution must be written in your answer booklet. Okay, draft is just for you to do some working. Okay, it's not for handing it, for marking. Okay, okay, right. In that case, let's start a new part. Okay, let's start with this substitution property here. Okay, so if f is a polynomial function or a rational function, then limit of fx is just equals to fa, provided that fa is defined. Okay, so why do we say that? Because how do you build up polynomial? Okay, polynomial are just scalar times some xn, and then you add up a bunch of different scalar times x to the different power, let's say n. Okay, so these are just using what rule? Using scalar, using some scalar multiplication, using addition, okay, using power, okay, in particular the product. So we can split all of them out. Okay, it's just a substitution. Okay, maybe we can test one example, right, that we have computed just now. Okay, so in particular, this guy here, this guy, 3x squared minus 2x. Okay, so just now we use limit law to compute. We get 40. There's a faster way here. Okay, if you want, the theorem say if you want to compute the limit of a polynomial, okay, the limit of a polynomial, when x approach a, what do? You just substitute 4 into x. Sorry, yeah, 4 into x, correct. Okay, so what do you get here? Still 40. You see, this is actually the last step you are doing here, you know. Can you see that? Okay, so we kind of shorten all these path here. Let's shorten all this path because we always know that this limit law will work. And then after the limit law works, actually you are doing substitution. And that's it. Okay. So we could extend this idea to rational function as well, because rational function is just quotient of polynomial function. Okay. So one very important thing here, provided FA is defined. Okay, you might think that maybe sometime the quotient you will divide by 0, then you can't use this substitution anymore. Okay, so it's very important here. You don't come and ask me, hey, he's saying I thought you say substitute will work. Okay, no, it's as long as FA is defined. Okay. Okay. If it is infinity, we also don't know what's going on. So it's okay. Okay, FA is defined here, meaning it is some finite number. Okay. All right. Okay, let's continue here. So let's quickly do this. Okay. So if you want to find the limit of this quotient of polynomial, what kind of function is this called? Margaret? Polynomial function. Rational function, right? Because this is a quotient of polynomial function. Okay, quotient of two polynomial function. So what can we do by the theorem? You just substitute. Okay, you just substitute. Can we quickly substitute and see what is the answer? Anyone have tried this? If you substitute, what are you gonna get? Well, basically, either you can use hand to compute or you just use calculator. Then you should get something like minus 11 over 2. Okay, so since this FA is defined, okay, so you see how the logic works backward again. Since this substitution is defined, then only this limit equals to the substitution you get. Okay, the logic is again a bit backward. Okay. Okay, how about the second one? Does it work? No. How? The substitution doesn't work. So can you still find the limit or not? The substitution doesn't work. So can you still find a limit? Then you need to use the old way again. Okay, so you need to use the old way again. So let fx equals to x cubed plus 3x plus 7 over x squared minus 2x plus 1. So how do you see that it doesn't work? maybe you can try and factorize your denominator. So this is one of the technique. Whenever you want to see these square quadratic expression, right, you can try and factorize it. So if you factorize it, do you get x minus 1 squared? Yeah. Okay, so you can see that this function is not defined at x equals to, okay. So the limit law also won't work. Okay, the limit law also won't work. So in this case, you need to use O, or the primitive way. What's the old way? What's the old way there? You must remember this old way. The old way will always work. So limit law also won't work because quotient, the numerator is the denominator is going to approach 0. So you just plot a bunch of numbers. Okay, what are the numbers you are interested in? Actually, 2, 2, 2. You want number that are close to 1, right? 2 is still a bit far, 0, Okay, 0 also far in the sense of this limit. You need to be very, very close to 1. Who say 1.1? Okay, 1.1 is already quite close, but you can be even closer. Okay, you can be more close. Okay, what kind of close you have? Let me move down a bit. Let me copy this. X of x, okay, equals to x cubed plus 3x plus 7 over x minus 1 squared. Okay, it's not close enough. Okay, you can do even closer. 1.01, right? 1.001. Okay, you must be super close, okay, to talk about this limit. Remember the picture I showed at the start of the class? Okay, we need to shrink our region between L, okay, such that there are points of fx, okay, that is close to this a here, a equals to 1 here, okay, still stay in the region of the limit. Okay, and then from the right hand side, what do you need to do? Sorry, left hand side, you consider, for example, 0 0.1, 0 0.001, 0 0.0001. Okay, I think for the purpose of this class, this kind of approaching is enough for you. Okay, this kind of approach. Okay, so if you do this, you could check that your function actually blow out to infinity. Okay, actually blow out to. Or you can the other method I ask you to double check yourself, right? Is you can plot with the GeoGebra. Okay, you can use some website to help you double confirm. Okay, no? Okay. Okay, let me try some method here. Maybe we haven't teach it yet. Let me try some method. Maybe later we'll learn some method. So let me try something special for you. Later we'll see it again. So how about use this second method? Let me try. Let me try this. So let's say I try this. Okay, let's say I divide top and bottom by x squared. Okay, everyone okay or not? If I divide top and bottom by x squared, so I'm multiplying by 1, right? Because top and bottom what I'm doing is like this. Okay, so actually I'm multiplying by 1. But the good thing about this is I make my function easier around 1. Okay, so let's see, is it easier here? Okay, if you look at all these functions, what are their limit when x approach 1? You look at x, what's the limit when x approach 1? 1. 3 over x, 3 over 1. 7 over x squared, 7 over 1. Then 1 is 1. 1 is a constant. Minus 2 over x, minus 2 over 1. And then plus 1 over 1. So you see how all these limit exist. So you can use the limit law to split out all the sum. Okay, so in the end, what do you get here? Does it work? Let me try. 1 plus 3 plus 7 over 1 minus 2 plus 1. Something divided by 0. Oh, don't quite work also. Okay, because everything exists, then which rule doesn't work? The quotient law doesn't work. Okay, why? Because this limit here will go to 0. Go to 0. So it's not good. Okay, because the limit of the bottom one is 0. Okay, so the quotient law doesn't work. Never mind. This one doesn't work. Okay. For question? Because the quotient law, you need to make sure that the denominator, the limit is not 0. Okay, but this is again 0. Okay. Never mind. We just stick with the old method. Okay. Any question so far? No. But later we will use this kind of trick, okay, to find limit. Okay, later we will see again. Okay. So next theorem. Okay. So what are we doing just now was actually this theorem. We replace an f by another g. Okay, it's fx and gx is the same. Okay, for all x in the open interval that contain number a. You know how to think about this open interval here. So let me remove this table first. Okay, so the picture is like this. So you got the f, you got the f like that. Okay, and then they are the same around the neighborhood of a. So open interval of a maybe looks like this. Okay, if I say this distance is delta, maybe one side is 1 minus delta, the other side is 1 plus delta. Okay, so if they are the same around this open neighborhood, maybe they can deviate at other places. Yeah, then their limit when x goes to a, if both of them exist, they should be the same. Does it make sense for this picture here? Okay, we don't really care how far, but this is another instance to tell you that limit doesn't care if it is too far from a. We don't really care. Okay, we only care when the value is close to fa or ga. Even if fa and ga doesn't exist, right, we still can look at this limit. Okay? Which we look at f of x where x is very close to a. Okay, very close. Okay, so the question here is this two having the same? Is this two a same function or not? Hmm? Any idea? Same? Why? Why do you say they are the same? Just factorize, factorize, okay, good. Let's see if we factorize. You get x plus 1. Okay. But on the other side, x plus 1 as well. Oh, seemingly the same. Okay, I challenge you, all of you. Try GeoGebra now. Plot these two. Yeah, try GeoGebra and plot these two functions. See whether they are the same or not. Oh, interestingly, GeoGebra cannot understand how. GeoGebra, GeoGebra, GeoGebra think that they are the same. I think this object is not good. This GeoGebra, let me see. Let me check first. Okay, okay, this GeoGebra think that they are the same, but actually they are not. Why are they no? Because very simple reason here. If you put 1 into fx, what happened? 0 over 0. Okay, actually it's not defined. But if you look at this kind of software plotting, they like to make in what the mathematical term is, make the graph continuous. They will fill in the gap themselves. Okay? This is also true when we do the higher dimensional plotting. They will fill out the place that's not defined. Okay. So okay, wait if you still remember the comment I told you last time, when you are doing this cancellation, right? When can you do this cancellation? Actually, this is true only when x is not equals to 1. Okay, because if when x is not equals to 1, for example, let's say if you give you an example, x equals to 2, you are really doing simplification, 2 plus 1 times 1 over 1. You are canceling out 1. This is fine. But when x equals to 1, what happened? Can you really cancel out? Can you really cancel out 0 over 0? This is not defined. Okay, you cannot really simplify. Okay, so the question here is, you see, the hint here is what their domain. Okay, what their domain is. Okay, so the first one, the domain could be x in R, but x cannot be equal to 1. But the second domain, you can put anything really. Okay, you can put anything really into this x here. Okay or not? Okay, so away from 1, like what your friend said, factorize, they look the same. Okay, so let's say we change this picture a bit. Let's change this picture. Let's say this a is already 1 here. Okay, so one of the function is like this. Okay, x plus 1 gx here. But how does fx looks like? It is the same away from 1, just that at 1 it is undefined. That's it. Okay, you are missing just 1 point. Okay, it's not showing. Okay, like, okay, so it's just differ by 1 point here, your fx. Other place is the same. Okay, but does this affect the limit of fx or not? No. Okay, the point, the exact value on the f1 here won't affect how it behaves at the nearby. It behaves the same as gx because it's the same term. But limit doesn't care about the actual. Okay, make sense? You see, so this line is very important, except possibly at x equals to a itself. Okay, except. Okay, equal and then except. Okay, it could be the case that FA not equal to GA. Still fine. Still fine. Okay. But all the nearby point must be equal. Okay. Okay. All right. So we'll use this to do a few exercises here. Okay, let's do uh, two of them and then we'll have a break. Okay, and then we'll come back again. So in this case here, in this case here, you'll see that if you use limit law, you get something like 0 over 0, which is not good. Okay, so we will try to modify our function first. Okay, so how to modify here? Do you guys remember a formula on difference of square? A square minus b square is what? A plus b times a minus b. Okay, so if you notice on your denominator, numerator, there is a difference of square, x square and 1 square. Okay, so you can try and factorize them first. X plus 1, x minus 1. Okay, so now ask yourself, can I cancel or not? We can cancel because we don't care about the point at x equals to 1. Okay, just nearby x equals to 1. If it is nearby x equals to 1, we can do simplification because x minus 1 is non-zero. Okay, so we can equate this limit to x plus 1. But you know the limit of x plus 1 when x goes to 1, which is 2. Okay, using the limit. Okay, so if I want to say, I would say that since x plus 1 equals to x squared minus 1 over x minus 1 when x is not equals to 1. Okay, these two functions is the same when x is not equal to 1. But it's already good for us to find the limit. Okay, because accept possibly the value at x equals to 1. Okay, happy? Okay, happy? Any question? Feel free to ask if too fast or what. Okay, let's do one more. So how about the next one? Can we play a similar trick here or not? What do you think? Can we play a similar trick? Okay, so how to factorize? X plus 4. 5, okay. X minus 2. And then x plus 3. X minus 2. Okay, so you would think that, oh, can I simplify them or not? Okay, can you? Where does the limit happen? At 2. But we don't care about 2. Okay, so we could just simplify it to x plus 5 over x plus 3. Okay, then what is this? This is just 7 over 5. Yeah, you can use the substitution property now because it's just a rational function. Okay, any question before we break? Okay, let's break until 10:03. Yes.
Okay, so forget which number was it, but I tried to like do some experiment where I used the hospital
Mm-hmm.
where I can try to prove whether it's actually infinite or not for the result, the limit. I know
Mm-hmm.
which number.
Mm-hmm.
But then I forgot about the what's it called the fundamental the what's it called the method, which is like we usually do derivative for like one time, right? Can it be repetitive?
Multiple times? Yeah, sure. You can reuse the L'Hopital rule.
No,
Yeah.
I mean like for like,
Yeah, sure. Yeah. As long as you meet the L'Hopital condition, you can keep applying the L'Hopital. Mm. I thought you know. Right, you need to get the L'Hopital segment first. I think either you get zero infinity over infinity or infinity over zero or something, and zero over zero. These are the three things you met. Then you can apply L'Hopital rule. Yeah.
number is oh this one. So uh, okay, the first derivative, sure, it's still
Which
infinite.
one? Which one? You
Like,
want to use L'Hopital here?
yeah,
You cannot use it
because
because it's not infinity over infinity or infinity
oh,
over zero or zero over zero.
also that's why it does not.
Doesn't apply here. Doesn't
Oh,
apply.
that makes
It's
sense.
not. It's not like you can do it for any cases. You need to do it for the infinity over zero case or zero over zero case or infinity over infinity. Only you can do L'Hopital.
That makes sense.
Mm.
Okay.
A lot of these formula, right? You need to map the condition first. Yeah, you need. Yeah, the condition is very important. Okay, for those who are here, I'll take attendance first. I'll take the rest after they come back. Oh, you want to take first? Yeah. Okay, what's your name? 刘俊杰. Oh, 刘俊杰. Where are you? Yeah, yeah. 常希和. Yeah. 陈乐天. Okay. 陈瑞阳. Okay. 陈若池. 陈诗曼. 陈意南. 陈意南. 意南. 陈玉涛. 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 陈义哲. 陈义哲. OK. 戴丽文. 邓瑞阳. 方泽汉. 方泽汉. 古家来. 何嘉诚. 吴佳怡. 黄奇军. 黄毅清. 季俊义. 孔祥思. 雷艺林. 雷艺林. 李冰珍. 李冰珍. 李家堂 you okay. Ling Hao Yun. Are you? I thought you are going to Huawei. Are you going to Huawei later? Ah, I see. Okay. Ling Wenqi, Liu Hangxiang, Liu Xingyang, Lu Wangda, toilet. Okay. Lu Xingyue, Luo Yuhen, Ma Yitian, Miao Bingchen, Ni Haoran, Desmond not here. Desmond Tan not here. Tommy, Luo Chongyi, Ang Yingjie, Islamova Anel, Gopagani, Arthur Suraya, Ariando. Oh yeah, you are Ariando. Okay. Hisham, Daniel, Hashim, Hashim, yeah. Madia. Hey, Hashim, okay. Madia competition. Bradley, Aaron, Brendan, Brendan, Brendan here. Okay. Alicia, Alicia. Gunakanti, Margaret, Khalid, Hassan Khalid, Jahel, I think not here. Jahel, Javed, yeah, no. Gabriel, Jeffrey, where's Jeffrey? Okay. Purity, front, okay. Chen Fan, He Yating, He Yating, not here. Yating, retake. Hu Huiye, oh Huiye, you are here. Okay. You are in the Moodle, right? Yeah, I'm update the all the content there. All right. There's something maybe I need to tell you. You will be learning MPU like writing for purpose or professional purpose, is it? Okay. So I guess you need to learn how to write email. Because I am getting email like without content. You just write your subject, or you write your content inside your subject. So the topic is like a paragraph, right? Okay. So you should write the paragraph inside your email, and then the subject should be like just some phrase that's suggesting what the email trying to say. Okay, don't put the whole paragraph inside your subject. Okay, it's like the topic. Can you imagine your textbook? The topic is like whole paragraph. How you gonna read that? Okay, so please put your paragraph into your content of your email. Okay, don't leave your email blank. And then I get some question on the exam midterm material, midterm scope already. We will disclose it again, okay, when it's close to midterm. But for now, it's following what we say in the course info. It's about until the derivative chapter. We finish everything on derivative or midterm, and then integration will be on. Anything after integration and integration will be on. And please do revision because quiz one is coming soon. When is quiz one? Please check. You need to plan your time. So when's your quiz one? When is it? Which week? Week four. Okay, now it's about week two already. So you still got one more week to do revision. Okay, so maybe next week we will tell you the exact scope about quiz one. Okay, but I think roughly it's about this week and last week. We will tell you next week again. So please do revision. There's one more week, 2 more weeks to quiz four. Okay. Right. Um, Let's give you 5 minutes to do this 3 question here, and then we will discuss. Try and check with your friends. This 3 question is inside the notes if you cannot see it. 2.20, 2.21, and 2.2. I give you 5 minutes to try. Anyone I missed your attendance just now? If you just came back from the toilet. Yeah. 019. Lý Y Linh. Luanda not back yet. Okay. Okay. Yeah. I suggest you make friend between your classmates because we will have a group assignment later. It could be individual, it could be group. And also because you guys are in the same degree, right? Okay, so there will be a lot of group assignment coming up also. Yes. Yeah. I will do one time. Okay. Don't double. It's not. Okay. Try. Okay, so for the 2.20, right? Can we use similar technique that we learned just now? Okay, so you realize that there are difference of square, right? You can try and start factorize first, see if we can do anything special here. Can we cancel out? Yeah, right. Okay, if x is not equal to 2, they are just non-zero, then you can simplify them. So this is actually a convenient way, okay, to do simplification, okay, for all x. So, what's the limit? Can you tell me the final answer? 1/4. Okay, good. So basically, you are evaluating limit of x plus 2, sorry, 1 over x plus 2 when x go to 2, which is 1/4. Okay, good. How about 2.21? Is it difference of 2 square? Is it difference of 2 square? No more difference of 2 square. So what can you do here? So someone suggested to multiply by square root x plus 1. This is what we call the conjugate. Okay, conjugate of square root x minus 1. But this is actually the reverse engineer of difference of 2 square. Okay, so if we look around x equals to 1, right, you can check that this function here is equals to square root. What am I doing here? Oh, you are using that way. Okay, so let's try your method first. So x minus 1 times square root x y over square root x plus y times. Let's see if this works. Actually, there's a some difference of square, right? What I say is not true just now. Why no one correct me? So let's try your friend's method first, see if it works or not. What's this? X minus 1. Okay. Wow, this also works, huh? So if x is not equals to 1, you still can cancel out x minus 1 where you get square root x plus 1. Just now I made the comment saying that the difference of square doesn't exist here. It's not true. Why is it not true? Can you find square root x or not? Okay. Uh, if is it logic that I write this? Is this logic? Huh? Logic? This is logic. But you should know that square root of x could be plus or minus, right? Let me ask you a question. For example, like, um, did you know this? Square root of 4 could be plus minus 2. Don't know. Don't know. Well, let me see. So how should I put this? Because minus 2 square is 4. 2 square also 4. Okay. How do you know where this 4 come from? Okay. So if you want to get positive, right, you need to stare at the positive side. Okay. Can we always stare at the positive side? What do you think? Can we stay of the positive side? Can or not? Do we care about negative x? Why? Because you only care around x equals to 1. Okay, so you can actually keep your x all the way greater than 0. Okay, so this is true when x greater than 0. Okay or not? Okay, so when x greater than 0, you can do this splitting. If you do this splitting, right, and x not equal to 1, you also get square root x plus 1. Okay, so these two way get the same function. Make sense? Okay. I think the method your friends give is better. It cover further region. Okay. If you use the difference of square, then you need to shrink your uh, domain smaller. Okay. So either way, we get that the limit of x to 1 of x minus 1 over square root x minus 1 is equals to limit of x to 1 square root x plus 1. Okay, so then you can use all the limit law which are available to use. Okay, then you get 2. Okay, any question or not? Feel free to ask question. It's not that everything I say is correct or you have to follow 100%. You need to learn to make your own judgment. Okay, so that you won't get scammed, right? Make sure that you don't get scammed because there's a lot of scammer in here. I mean, around here. You know that? You know that there's scammer appearing in the school compound. Someone asking for donation, and then people just donate because they thought they are kind. But people are not using the donation properly. Do you guys follow the student council account here? Yeah, they do post this kind of a reminder post. Right? You could follow the student council. Okay. Another thing is China embassy will call you saying that you have some convict, some crime, and then ask you to pay some fine. Yes. So be careful. You thought that, oh, China embassy call me. You think it's very like the authority calling you, right? You need to follow. But actually it's scam. Okay, so you need to make your own judgment. Okay. This is a true story. From another course. Another lecturer shared to me. His student got scammed by a so-called China embassy call. Okay, so-called. Okay. How about we left 2.22 as an exercise? Similar method. Okay, so this one as a homework. Okay, try and do it yourself. Actually 2.22, 2.23 up to 2.24, right? We actually come across this kind of calculation already. We find left, find right. If they are equal, then the limit exists. Okay, maybe we choose to do one of them. Okay, and then the rest we will left as an exercise. So let's do. How about you pick one? My choice is 2.24. Okay, let's see what kind of choice you want to do out of these four. Which one you want to try, or want me to try for you? Which one? You pick one, then we will do together. Huh? Which one? You think? I don't know how to do. I don't think so. Is yeah, the one that you're most unsure. 2.23 up to 2.26. Which one? Pick one. Pick one. Quick, quick, quick. 2.25. Huh? Okay, let's try 2.25. How about do 2.24 also? That one is my pick. So we do two lah. Okay, we do half of them for you. Okay, let's do 2.24 first, and then we will do 2.25. Huh? Okay, so if we're gonna compute this limit of this function from the left, do you still remember what's the definition of absolute value? When x less than 0, from the left, what is absolute of x? Minus x, good. So this function actually equals to minus x at that region. Okay, but in this case here, you are just evaluating a constant function minus 1. So in this case, you will get minus 1. Okay, how about from the other side? Okay, due to the piecewise definition of absolute x, it is just x on that side. Okay, so on that side, you are just computing the limit of the constant function 1, which is 1. So these two are not equal. So limit doesn't exist. Okay. So the limit doesn't exist. Okay, how about the second one? All right. I strongly suggest you plot this out. Okay, sketch it, and then or you use GeoGebra to help you. Yeah, please learn to sketch. And then check whether your solution matches up with the picture or not. Okay. How about fx equals to square root x minus 2. All right. So how does this look like in the picture? So let's pick the stick here. When x is less than 6, you use x minus 4. So what's x minus 4 here? Basically, the basic shape is the linear y goes to x. Okay, and then you move down by 4. Okay, move down by 4. So where's the y-intercept? When x equals 0, which is negative 4. So somewhere like here. And then you draw it up. Okay, something like that. Okay, we don't know what happened at 6. Okay, we will try and figure it out. Okay. And then how about square root x minus 2? Okay, so the basic shape is square root x. Okay, but x minus 2 shift the graph to the left or to the right? To the right, okay, because if you put 2 into it, it's just the original 0. So you will do something like that, okay? But I start all the way from 6. So the front part should be cut, okay? You should cut the front part here. Okay, now we will figure out what is their limit, okay, at 6, when x approaches 6. Okay, let's do it. Which one you want to do first, left or right? Plus or minus? Choose one. You need to do both anyway. Choose one. Plus or minus? Minus, okay. So let's try the minus one. So the minus one, so you should use the first function or second function here. Second, okay, because you go from negative. So this is limit of x to 6 minus of x minus 4. Okay, but this function is just a polynomial function. So what property you can use? Substitution property. Okay, so you just use 6 minus 4, which is 2. Okay, so in this picture here, there's something wrong I draw, right? Because it should approach where? Approach 2. Okay, but here is negative, so we should change our graph a little bit. So let's change it. Change it. Okay, so we need to go up. Maybe reach to 2. I don't know whether they reach the same point or not. So to differentiate, how about we make this a 2 first? This is for sure 2, so let's keep this as a 2. Okay. Okay, let's do the other side. Okay, if I approach from the other side, this function change, it will become the square root function. Sorry, yeah, this is plus. Okay. Does this commute? Commute or not? Okay, because limit of x go to 6 plus from x minus 2 is what? 4. Okay, so the limit exists, so we can commute. Okay, we can bring the limit into the square root. So let's bring the limit into the square root, which is 6, sorry, x minus 2. I'm a bit too far ahead of myself. So this case, this is, because x minus 2 is a polynomial, we can use substitution property. So 6 minus 2 is 4. Square root 4 is 2. Okay, so in this case here, you can see that actually this square root also connected to this 2 here. Okay. Maybe you could ask the question just now, right? Hey, I thought you said this square root 4 could be plus minus 2. Can I choose minus 2? Can I choose minus 2? Why can't I choose minus 2? Because the definition of the square root x is always positive. It won't go to negative. So there's no square root x around negative number. So you cannot pick negative. Okay, so this is the subtlety of our square root function. You need to keep in your mind is we define our square root function. So this one you need to keep in your mind. So we define square root function to be positive. Okay, we don't choose the negative one. Yeah, so that's why the square root function of this. Yeah, all the root function is positive. Okay, this is what we set. This is how we define it. Okay. Otherwise, we should like draw like this already. Okay, but that's not happening. Okay, so this is definition. Okay, any questions so far? Question? Oh, okay, so please do 2.26 as well. This is the double bracket x, which is the greatest integer equal or less than x. Okay, Another property of limit is if you know that one gx is greater or equals to fx, okay, around the open interval that contain a, except possibly at a itself. A itself can happen anything. We don't care actually. Okay, what we care is around a. Around a is very important. Okay, around a is very important. And then you expect that the limit of gx is always greater or equal to. Okay or not? Do you have picture in your mind? You must have some picture in your mind. So for example, fx like this. Okay, let's say the easiest one is like this, gx like this. Greater equals to, let's say, okay, give it a name, f here, g here. Okay, if I want to look at the limit when x go to a, you will see that the first limit here, let's call it L1. The second limit, call it L2. L1 is always greater or equals to L2. Okay, clear? Make sense, huh? Okay. All right. Then next, using this, we will have a theorem called the squeeze theorem or the sandwich theorem. You know what sandwich? So you are like squeezing, right? You got two bread, squeeze your meat inside. I think you should know, right? You love McDonald's. I think all the students here like to go to McDonald's. Okay, so you must know this hamburger, okay, or sandwich here, squeeze. So let's say your GX here. So who is squeezed here? GX is squeezed by FX and HX. Okay, HX is greater or equal to GX, and then GX is greater or equal to FX. So it gets squeezed by these two. So in this picture here, maybe I should draw like this. So get the other color. Okay, how about this color? Okay. So GS is squeezed. So let's call this G instead. And then this is F, like that. Okay, squeeze. Again, for all x in an open interval containing number of a, except possibly at the number a itself. So at the a itself, gx could be greater than fx or smaller than fx. We don't care. Okay, what we care is anything beside a. Okay, must be squeezed. Okay, you get what I mean? So for example, maybe here is nothing, here is nothing, and then here also nothing. Maybe G I can define piecewisely like this, and then F maybe I throw it down, and then red one I throw it up also can. Doesn't care. But what I care is around here. So around here is very important. Okay? Anything around here, except at A. Okay, one more condition, very special, this condition. Okay, this condition will make things work. Otherwise, it won't work. So let me highlight it. So this condition here. What does this mean? Limit of fx equals to limit of hx equals to y. What does this mean? From that picture, can you tell me what it means? From that picture, can you tell me what it means? At x equals to a, the limit of f and h, the two break, right, have to equal when x go to a. Can you translate to that picture? What could happen? L1 is the limit of f, right? When x goes to a, f, eh, why I name it f? This is supposedly to be, which one is f? Okay, the top one should be h. Okay, so the limit of h is L1, limit of f is L2, but the theorem says what? These two number has to be the same. Okay, so what happened to that picture? L1 have to equals to L2. Okay, so meaning what? Meaning I should draw something like this. Oh, this one get rid. This one also get rid. This one also get rid. This one also get rid. So meaning when f approach x a, fx should approach to some number here. Okay, let's call this number L. So this one is L. And then the limit of hx also approach to L. Okay, like that. This one can throw away already. Okay, such that all the limit equals here. Okay, can see what happened? Okay, then what can you deduce here? Then we can deduce the limit of gx. So this is the thing that we are interested. Okay, the limit of the middle function is what we are interested. What is it? It is also L. Can see from the picture, it must be L also. Okay. Away from this point, it is squeezed, and then when the limit come close to A, they have to be the same. They should agree. Okay. So to apply this squeeze theorem, right? What do you need to know first? Okay, there are two things to know. One, you need to know this squeeze property here. Okay. Second, you need to know the limit of the greater function and the smaller function. Okay. Then you can know the limit of the middle function. Okay, so far so good. Okay, so that's why you got this picture here. Okay, you can see that this picture got some extra hack here. You see this G is not squeezed when x is less than 0. Okay, but that's fine. That's fine. We only care about open interval, small interval in particular around A. It has to be true. Okay, not? We only care about close, very close number near A. All right. So let's do this question here. Okay, so how do we apply the result here? So can we squeeze anything here? Anything that we can squeeze here or not? If you still remember our sine graph, how does our sine graph looks like? Okay. Does our sine graph go to infinity at any point or not? No. Okay, but what's the largest value plus 1? The smallest value of sine can get -1. Okay, so one property you need to keep in mind is the sine function. Okay, no matter what you put inside here, it has to be greater or equals to -1 and less than or equal to 1. Okay, so from here, you can build our function here. So you know that our function x squared here will be squeezed with x squared and minus x squared. Okay. Okay. Makes sense. I multiply x squared across. Okay. Then now it's the squeezing property. So to use squeeze theorem, we need to check what's the limit on the two function. Okay, that you use to squeeze your middle function. Okay. So do you know what's the limit of minus x squared, for example? This is just a polynomial, right? Okay, so you can use substitution, right? Okay, so this is 0. How about the other side? Limit of x to 0 of x squared. This is even easier. Also 0. Okay, so by squeeze theorem, the middle function also have to go to 0. Okay, so what's the picture here? I think I got a picture here. Let me show you the picture. Picture is like this. So the picture is like this. Okay. So the two squeezing function is x squared and x. And then your middle function is like jumping and then getting small. You see? Remember the example I showed you last week? The oscillating 1 minus 1, why the limit doesn't exist, but this one exists because it gets squeezed by two function that has limit added. Okay or not? Okay. So any idea for the next one? Can you recognize that you can use similar technique? Okay. Limit of minus x is what? Also 0. Limit of x is also 0. So in this picture here, instead of getting this 2x squared, right? Okay. What you squeeze is, what you used to squeeze was these two function here. So one is y equals to x, the other is y equals to minus x, like that. Okay, so your function also jump between these two, like that. Yeah. Okay, your function also jump between like this. Okay, make sense? Okay, so try and do it yourself for this question here. Okay, this one with homework. Okay, any question before we left this limit chapter? Any question? Any question before we leave? Yeah. So what we learned was the idea of limit. Okay, close but nearby point and then see what happened to the value of f. And then second is we learned a bunch of rules, limit laws, and then substitution property, and then squeeze theorem. Anything else? That's it. So you could try if you could use the law, or you need to go to the primitive method where you need to plot it, or you need to see what's the behavior of the point. Okay, question or limit? No? Okay, then we will start a new subtopic here, which is called the continuity of function. Okay, so we say that f is continuous at a if limit of fx equals to fa. Okay, actually there are three things implied by this statement. Although you see that, oh, this is just checking the limit equals to fa, but there are really three things happening here. So first thing is fa has to exist first. Okay, must be defined. Okay, second, defined meaning is some finite number. Second, you must be able to compute your limit. Okay, so the limit of fx must exist first. Then these two number must equal. Okay, so that really there are three conditions here. Okay. Otherwise, I will say that f is discontinuous at a. Okay, does this match your intuition? Continuity, continuous. I think one definition of continuity is you can draw the graph without lifting your pen. Okay. For example, this graph here, I cannot draw this graph without lifting my pen, right? Because you see, when so let's check this f here. When limit x go to 3 of f, let's say this is f, okay? Does that exist or not? Does it exist? Okay, go see your 3 here. Does it exist or not? Why? Why not exist? Yeah, why? Mhm. Good. Okay, so what's the left limit? Yeah, what's the left limit? Hey, I don't know what is this, right? Some negative number. Okay, some negative number. So maybe say less than 0. Okay, how about the right limit? Some positive number. Okay, negative number and positive number always not equal. Okay, so the limit of f go to uh, x go to 3 does not exist. Okay, so you can see from the graph also left and right doesn't match up. Okay, so in this case, f is discontinuous at 3. Okay, how about let's look at another point. Limit when x go to, so this is first one. Let's do the second one. So how about limit x goes to 1 of fx? What happened? The limit exists or not? Kind of connected. Connect where? Somewhere greater than 0. But can you get what is f1? Any f1 exists or not? Any f1 exists? Got f1. Do you understand what this dot means? What does it mean? Nothing. Kosong. Nothing. Right. Okay. So f1 is not defined. Okay. So f is discontinuous or is not continuous at x equals to 1. Okay. Also not continuous there. Okay. There's one more point f is not continuous. Where? 5. Okay. What happened at 5? Okay, so I think we should keep all the definition away first. And then how about we rename this number so that you don't get confused. So this is number 1. This is number 2. Okay, let's look at number 3. Limit of x to 5 exists or not? Left and right. Do they match up? Left limit, right limit. Match up. Okay. Exists. F of 5 defined or not? Hello. You finished your competition? Wow, so fast. Okay, so f of 5 exists or not? Exists, right? There's a black dot here. This is the f5. Okay, it's defined. But do they equal? No. Okay, they are not equal because which one is greater than which? But f5 is greater than limit of x to of fx when x go to 5. Okay, so they are not equal. So f is discontinuous. Hey, why my dis and continuous split up? Discontinuous at x equals to 5. Okay, so you can see what kind of possibility could happen. One of them is the limit doesn't exist, although it is defined for f3 here. Okay. So should I add one more here? Here, although f3 is defined. Okay. And actually, f3 is equals to the left limit in this case. Okay. So either they split up, the graph split up, split away, or there's no point to connect them, okay? Or the connecting point jump away. Okay, these are the 3 ways that a function cannot be continuous. For the simple way, I would say these are they are more exotic examples. If you come to MA, you will see more. But other than that, the function should be continuous. Okay? So if you look at any other x, for example, which x is continuous, maybe give one from my right hand side. What's your name again? What's your name? Yeah, right. So can you give me a point where f is continuous? 2. Okay, so if you go from the left, from the right, okay, they meet up, and then fa is defined. Okay. Can we give another one? How about the next guy? Can we go around the first row here? Tell me any continuous number. I mean, place. When x. Go there, go there. Yeah. 1. Okay, 1 also. 1? We just showed that 1 is discontinuous, right? Sorry. A bit away from 1 also can. Where? 0. Okay, 0 works. Yeah, 0 if you go left, go right, and then meet up. Okay, next one. U. Yeah. 4. Okay, 4 also works. Okay. Another one. Continuous point. Where is F continuous? Pick one number. 5. 5. We just showed that 5 is discontinuous. 6. No 6 or cannot check. Pick something between 0 and 5 so that we can check. Huh? What? Choose another one. 0 between 0 and 5. 6 I cannot check. 3.5. Yes, here. Okay, so you go from left, go from right. The limit exists. And then f of 3.5 defined at the same point. Okay, next one. 1.5. Good, very good. Next. Sorry? 4.5 here also works. Okay, next. 0.5. Good, very good. Every 0.5 come out already. Yeah. Next one. Yeah. 3.5 already chosen. Huh? Sorry? 4. 4. Good. Okay, next. 4.5. Okay. Next one. Also 0.5. Last one. Which point is continuous for F? Yeah? Yeah, you pick one point such that F is continuous. Sorry? Pick one point. Some number between 0 and 5. Pick one. 2? 2 here. Yeah, 2 is fine. Okay? Yeah. All right. So let's try some examples, some other examples here. So is this function continuous at x equals to 2 or not? No. Why? Huh? It's not defined. Very good. So not f is not defined at x equals 2. Then you don't even need to check the limit already, right? Checking limit is very troublesome. Okay, so first you need to ask yourself whether your function is defined there or not. Okay, if it's defined, then only we can check whether the limit agree or not. Some of the students, they go and check the limit and then already finish 10 minutes. They've just found out that it's not defined there by substitution. Okay, so you need to take care of your timing when you do exam, for example. Okay, find the easiest way to answer the question. Okay, how about next? Continuous or not? Continuous? Huh? Yes or no? No? Why? Sorry? Yeah. The the one beside Jian Tong. You? Continuous or not? You. Yeah. What's your name? I can't remember your name. Huh? Hello? Hello? Do we have this name? I thought I called you a different name just now. What's your ID again? 2509 082. Oh, Chengdu. Okay. Okay, Chengdu. So is this continuous? Yes, sir. Why? Sorry? If you substitute, you get 0. But isn't it you divide by 0 also? It's not defined. Okay, so sorry, is this continuous? Good. Okay, so again, f is not defined at s equals to 2. So this is also another mistake student will make. You just substitute 2 into the numerator or 0, then you are happy. But you didn't realize that you are divided by 0 as well. Okay, so it's undefined. Okay, so f is not continuous. Can you quickly see that the limit when x go to 2 actually exists, correct or not? Use the difference of square, okay, which is what? The limit is 4. Okay, 2 plus 2 is 4. But too bad, f is not defined there. Okay, it's not defined there. Yeah. Yeah, Felicia, can follow? Okay, it's not defined because 0 over 0. Please remember this. You cannot divide things by 0. It's undefined. Can I do 0 divided by 2? Does this work? 0 divided by 2. What is 0 divided by 2? I got a 0 cake. I want to give you. Do you get anything or not? You get nothing. So it's 0. So this works. Okay. So the problem is you cannot divide by nothing. Okay. It's not about nothing divided by something. Okay? Is anything divided by nothing is not defined. Okay. So 0 divided by some finite number is defined. Yeah? Okay. So these are the small things you need to keep in mind. How about this? 2.31. We do some modification here. We do some modification. We understood that that function x squared minus 4 over x minus 2 is not defined as x minus 2. Sorry, x equals to 2. So we do a piecewise definition. I add in a point. Okay, I add in a point artificially. Okay, I add it in. So what happened here? Now f2 is defined now. Again, not that. f2 is 2. Okay, but from the previous calculation, we know that the limit of x squared minus 4 over x minus 2 when x goes to 2 is similar to the limit of which function? Which function? X plus 2, because we can do simplification when x is not equals to 2. Okay, so if you do this calculation, what do we get? We get 4. Still fail. Because the limit is not equaling to the function that we define. Okay, still fail. Too bad. So f is discontinuous at s equals. Okay. So up to this stage, do you know what you need to put at x equals to 2 to make it continuous? Can we replace this 2 or not? Replace to what? To make this function continuous. 4. Okay. So for the next question, it asks you how to define the c here. Okay. So actually you need to set your c to be the limit of f, which is x squared minus 4 over x minus 2 when x go to 2. Okay, which is 4. Okay, to make this function continuous. Okay or not? Question? Any question? Okay. All right. Right. Okay. How about this? 2.33. How to find the points of discontinuity of fx equal to sine x over x times 1 minus x. Okay. So one place to find discontinuity was to find where this function is not defined. Where is this function not defined? Where is this function not defined? Where is this function not defined? 0 and 1, good. Okay, it's not defined at x equals to 0 and 1. Okay, because if you put 0, you divide by 0. You put 1, also divide by 0. Okay. 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 Any other place is not continuous. Sine x is continuous at every point. X is also continuous at Oh, so you should think about 1 over x. Where is it continuous? It's continuous away from 0. Okay. 1 over 1 minus x is also continuous away from 1. So all together here, altogether, altogether what? Also, for a is not equal to 0 to 1. So if you try to compute the limit of x to a sine x of x 1 minus x here, you can just do a substitution here. Okay. Because your function, which is fa, as sine x is continuous everywhere, and then 1 over x is continuous when x is not equal to a, and 1 over 1 minus x is continuous when x is not equal to 1. Sorry, this a is 0. Okay. So other than 0 and 1, they are all continuous. Okay. So it's just f of itself. Okay. So altogether, hence, x equals 0 and 1 are the only point of discontinuity. Okay. Any question for this one? Any questions so far for this one? Oh, okay. How about next one? Here. This continuity of greatest integer function here. If you look from this graph, can you find the discontinuity point? Where are them? Okay, maybe start from this row. Give me one discontinuity point for this function here. Like, one by one. 4. 4. Okay, so if you look at 4, the left limit and the right limit is different. Okay, next one. Huh? Pick one number. No, already chosen. 3. Okay, so look at 3. The left limit and the right limit is not equal, doesn't exist. Okay, so discontinuous. Next. 2. Okay, 2 similar. Next. 2.5. Good, very good. Finally choose something different. So if you go to 2.5, what happened? The left limit and the right limit equal or not? Equal, or this is a horizontal constant. And also at that point, is it defined or not? It is. And they are the same. So 2.5 is a continuous point. It's not discontinuous. I want discontinuous. Can you pick another one? Huh? Huh? 1. Good. Okay, so if you look at 1, left and right, jump. Next one. Where's the discontinuous? 1.5. Good. Another 0.5 come out. So if you look at 1.5, what happened? Left and right limit is the same and also defined there. So it is continuous. I want discontinuous. So we'll pick one more. Pick, hey, look at here, look at here. Don't look at the sky. Sky don't have answer. Here got answer. Pick a discontinuous point. 2. 2 is chosen already. Basically, 1, 2, 3, 4 get chosen already. Pick another one. -1. Okay, good. So if you look at -1 here, left limit is -2, right limit is -1, so it's not equal. Okay, next. 0. Okay, 0 also work. So left and right limit is different. Next. -4. -4. Because I don't have the right limit. But do you know what's the right limit here? I think you should know. What's the right limit? You choose -4. You should tell me what's the left limit. What's the left limit? Good, very good. So actually this graph look like this. Okay, next one. I think still got some choices. -3, good. Also got a jump there. Okay, very good. So what did you notice? Where are the jump? The jump happened at the integer number. All the integer number. Okay, so uh all the points of discontinuity of f are the integer number. Okay. Okay, other than the integer, they are continuous. Okay, like your friend picked 1.5, 2.5. Okay, those are continuous. Okay, so what's the reason? Because lim of x go to n of this double bracket x here does not exist. It doesn't exist if n is an integer. Okay. Any questions so far? Question? No? Any question? Okay, if no question, how about we take a break from here? Let's come back 11:10. Hey,
When is the week four?
week 4, Monday.
Which day?
I think, but Monday is a holiday, so I think we will put it on Tuesday.
And what's the date? Let me check.
What's the date? I think it's 21, 21st.
Like,
Why?
I got a family too, and I have already booking the flight.
But we are 24 hours. Please.
Oh,
Yeah, it's not in class.
Oh,
Is it okay?
online.
Yeah, online.
It's online.
Yeah. You can submit or not.
Very good. Whether
I think it's
one play online.
yeah. So I think we fixed like starting from afternoon, maybe 3 to another day, 3 p.m. 3 p.m. to 3 p.m.
Okay, then
It should be
okay.
fine. Yeah. I think you should have at least 12 hour.
Yeah, I got time.
Yeah, yeah.
I will.
This is morning, right?
Yeah,
Yeah.
morning
We still have until 3 p.m.
until
3 p.m.
afternoon.
Yeah. I think it's a Tuesday,
Then
3
we'll do
p.m.
it.
to Wednesday.
Then we'll do it
Wednesday.
once I arrive.
Yeah. It's an offline.
Online, okay. Okay, another question.
Okay.
Because I'm reading this course.
Mhm.
I don't attend. Didn't attend the first week.
Sure.
What do we learn?
I already upload on the Moodle. So
Yeah.
every week I will upload the lecture notes.
Okay.
And then I upload the recording.
Yeah, I know.
So you can watch the recording.
Okay, basically tell me what is about week one like.
Week one is about function. And then this week we are just entering limit. That's it.
Okay.
Week one is all functions.
Okay.
And then the week two is limit.
The question about
Yeah.
The problem is just mentioned.
Mhm.
Okay, let me check what it is. What does this mean?
What do you mean?
Why do we need to mention limit of x?
Okay. Because we want to check continuity. So the definition of continuity is this one.
Yeah, I know.
So we need to like make sure this is true.
Yeah.
So this is what I do. You can check. This is what I do. So I make sure that this equal this.
Oh yes.
Okay. The reason is this. Because f sine x is continuous here, and then we can use lim. Actually, there are a lot of limit law happening here.
Oh,
Yeah.
actually,
Mm-mm.
the limit
Yeah.
limit at x equals a is equals to fa, and anyway, besides
Yes,
x equals 0 and 1,
yes.
since these 2 points are not defined.
More than that, these two is not defined there. Also, these functions are continuous there.
This function
Yeah.
continuous.
So that I can put all these things together.
Then we can prove what?
We can prove this equality here. Otherwise, you cannot just substitute.
Okay.
Right? Because let me write a bit more. So wait. So wait. So, because this line means that this line means that limit of x to a of sine x is equal to sine a. And then this line means that limit of x to a, where a is not 0, 1 over x is 1 over a. Similarly for this one. Then we can use limit law to put three things together. You understand or not?
Oh yeah, I understand.
Yeah. So that's why this is true.
Yes.
So it's all this plus a limit law with that. Does it make sense?
Yes, it makes sense.
Make sense?
Mm.
Yeah, because you can see this as sine x times 1 over x and 1 over 1 minus x.
Yes.
And you can
But for sine x, it is defined everywhere.
sure. It's also continuous. More importantly, it's continuous.
And for this two, it's also continuous.
Yeah, sure.
Anywhere besides
Beside
the
the
point is not defined.
Yes, good. That's right.
But the goal of this problem is
Is
to
to find all the discontinuous points.
discontinuity.
Yeah. So other than
why,
these two
why do we
points,
just need this step?
no, you need to like okay. So this step is like telling you these two are discontinuous, but how do you know these are the only two? So you need to make sure the rest are continuous.
Oh,
Correct or not?
oh, correct.
Correct? Yeah.
Yeah. My question is, this just.
Oh, this is the question. Okay, sure.
Yeah, this is
Okay, thank you. Yeah.
Okay.
Okay.
So other than that, it's proof.
There's no other point of
It's
view.
proof other than these 2
This way
points.
that
Everywhere is
it's
continuous.
Yes.
Oh, another question.
Yes.
I always distracted
No, it's okay.
because it's my first time on the class.
Okay. Yeah, sure. Actually, you can ask directly just now because I think others will have the same question. So it could help understanding.
Yeah.
Yeah, it's okay.
Right.
Just voice. Yeah, it's
Right.
fine. It's fine. That's fine.
I'm worried about this will interrupt him.
I will stop you if I think that you are disrupting me.
Okay. Okay.
If your question is good, actually, they will help. It will help them
Okay.
as well. Okay.
Okay. I
Any
think.
more? Yeah. Okay. Okay. No worries. Okay. I think your friend asked a very good question. Why after I check that there's two discontinuity point here, I still need to check other place are continuous. What do you think? Why? So is it enough to just say that oh these 2 point is discontinuous and then that's it? Then these are the 2 point. Yeah. Yes. How about 0.5 then? So you need to check, right, whether it continuous or not. So the next step here, so let me split it up. So first, we found that these 2 point is the points of continuous, but you need to determine all. So you need to check the rest is actually not a point of discontinuity. So we conclude that these are the only discontinuous point. Okay, does it make sense? Okay, if you just do step one, you just tell me that oh these 2 points are discontinuous. How about the rest? 0.5, 0.1. So you need to check for all of them. So this is how we check for step 2 here. Okay, so actually, if you realize step 2, actually we are hiding some limit law here. Okay, why? Because the reason we put continuity here is actually we know the limit at this point. And then we can speed up this function using this product. Then you can use your limit law again. Again, to compute the whole limit here. Okay, you can use the limit law. Does it make sense? Does it make sense? Okay, you know the limit of individual function. Once you know the limit of the individual function using the limit law, you can take the product of the limit. You remember the first hour? Yeah. Try right now. Try right now to make sure what you think and what I say is correct, huh? Okay, so what I meant is this. So I can compute the limit of this function as the product of limit. Okay, since these three products are coming from continuity, we know how to compute them. Okay. Make sense? Make sense? Okay. So if you further ask me, hey, why are they continuous at these points? Then you need to repeat our step. Go and do the left right thingy and then check the definition at that point. Okay. So you need to check the three criteria. Okay. Does it make sense? Yeah, but in exam, as long as you can write until this stage, we know what is happening. Okay. For yourself, for understanding, if you still don't know why this, for example, 1 over x is continuous, where x is not equal to 0, you should show it. Okay, do it as a example. Okay, do it as an example like how we did for all the function before. Okay? Okay, yes. All right, let's continue. So similar for function, we can define, sorry, similar for limit, we can define what is left continuous and right continuous, meaning you just check every point from the left. If it is left continuous, then the left limit should be equal to FA. Right continuity is the same. If you check for the right hand limit, okay, of fx is equals to FA, then we will say that it is right continuous. Okay, so you might think that what's the use of this thing? So for example, right, let's say our function is just defined like this. Okay, let's say this is 6, this is 0. Okay, so we will ask that whether it is left continuous at 0 or not, for example. Sorry, right continuous at 0 or not. Okay. Let's say this is L, this has to be L. Okay. if let's say let's say I put this at 0, but it jumps, okay, it jumps up, maybe jumps up a bit, then it is not left continuous anymore. Okay, if I define precisely like this, then it is not, sorry, in this case here, maybe my L, maybe I put it K here. This is L, but not equals to K. Then it is not left continuous anymore. Okay or not? So you should imagine that we define this kind of thing is like to take care of the boundary. Take care of the boundary. Okay. So do we have similar idea of this left-right continuity like our limit or not? Like if left and right agree, then we have a limit as this. So it is same here. Okay. So if f is continuous on an open interval, if it is continuous at each point of that interval, and it is continuous on the closed interval AB, if it is continuous on AB, open interval AB, and right continuous at A and left continuous at B. So this is the picture I draw here. Okay, so let's say we replace this by AB. Okay, and then yeah, good. So if it is continuous inside here, but you want to increase your number of continuous point here. It happens if it is left continuous at A or right continuous at B. Then this A, B are also the continuity point. Okay. A question so far? Okay. Okay. Let's look at this special function here. This special function is how to say, it's very special. Special function is very special. I mean, like, this is one of the type of function that you want to know. Okay, in particular, when you go to calculus 2, you'll see this a lot actually. How to read this function actually? Okay, I think 1 minus is pretty, how to say, pretty normal operation that you did to a function. If you minus this whole part here, right, square root function here, what you get is the reflection across the x-axis, and then 1 there will add 1 to your y-axis. Okay, so you shift up. But what is square root 1 minus x squared here? This is a little bit different from square root x, you know. Okay, this is a bit different from square root x. But anyone know how to draw this? Anyone has any idea? Okay, so let us try something different. So let's square root 1 minus x squared to be y. Okay, it's some number. But what does this number has to satisfy? If you play a bit around this equation here. So for example, you can square on both sides. Correct or not? Okay. So you get something like y squared plus x squared equals to 1. Have you seen this kind of equation before? Sorry? Yeah. What? Say? Six. Circle. Okay, good. This is actually a circle. What kind of circle? Radius 1. Okay, radius 1 circle. Another way to see circle was, you know Pythagoras theorem? A squared plus b squared equals to c squared. So this tells you what? The x coordinate and the y coordinate. What's the length of the hypotenuse? X here, y here. So here is 1. Okay, so this xy coordinate will satisfy radius 1 from the origin. Okay, so that's why you make a circle. What are circle actually? circle are all the points that are equidistant from the center. Okay, so this is the why we got this circle. But do you think that we really get the full circle? Do we really get the full circle or not? Why no? Why not? Sorry? That's not function. Good. Okay, one way to see that this is not a function. To check function, what's the test we use again from last week? Vertical test, right? Vertical line test. So if you draw vertical line, other than this -1 and 1, you always get 2 points. Okay. So the point here is this y equals to square root 1 minus x squared, right? Must be something on this circle. But what's that thing? From where to where is this function? From where to where? From where to where? Remember, I told you that if you simply work from this y square equals to y square plus x square equals to 1, you really get what? Y equals to square root plus minus 1 minus x squared. Okay. So in fact, you actually split this circle into 2 parts. Okay. One part is square root 1 minus x squared. The other part is y equals to negative square root 1 minus x squared. So where is negative? Where is positive? From this picture, can you see where is positive, where is negative? Y, where's your y? Y axis is here. X axis is here. Where is positive? Where is negative? Anything above y equals to 0 is positive. Anything below y equals 0 is negative. So in our case, we will pick the upper semicircle. Okay, so this is our square root 1 minus x squared. Okay, this one. Okay, but in the real function, what do you consider negative of that? So meaning you have to shift it down, I mean reflect it. So actually you pick the bottom one. And then you add by 1. You shift up by 1. Okay, so what happens if you shift up by 1? So do you know what these number here? So this is 1, 1, minus 1, minus 1 actually. Okay, if you plot it properly. So the real function here is shifted up by 1 of the lower semicircle. So it is something like this. So this is your fx equals to 1 minus square root x squared. Okay, so what's this height here? Yeah. So this height here should be 1. Okay, and then how about these 2 points here? One is -1, one is 1. Okay, let me remove the additional graph here. Okay, everyone happy with plotting this? Okay, happy? Or question? Okay, so what's our job here? Wow, continuous on interval of -1, 1. Okay, so how many things we need to check? We need to check the endpoint. We also need to check the point in -1, the open interval -1 to 1. Okay, so for a in -1 to 1, actually there's only one treatment you can do here. Okay, because in -1 to 1, this function looks like, okay, why this come out again? Okay, so this looks like 1 minus square root 1 minus a squared. Okay, so for all these points, right, actually you should notice that, what should you notice? You should notice that the square root function is continuous there. Okay, so that you can use this 1 minus square root of 1 minus a squared, which is fa. Why? Let me put a reason here. Because 1 minus square root 1 minus square root of 1 minus a squared is continuous at a, which is in between -1 and 1. Okay. Is everyone happy with this continuity or not? Or you have question? You have question? Any question on this continuity? So you need to use the limit law to check. Okay, you have to use the limit law to check. Should I check for you, or you understand what I say? Wait, let me think first. Okay, how about I show you one example, and then if you are okay, then we are okay. So let me put some example here. Let me pick A to be, let's say, 0. Okay, let me pick A to be 0. And then what is x to the 0 of 1 minus square root 1 minus x squared? Okay. So do you know how to find this limit here? 1 minus square root 1 minus x squared. Can we use limit law or not? Can we use limit law here? Why? Limit of x to 0 of x squared exists or not? Exists? X squared. X squared. Which is what? 0, right? Okay. So this limit exists. Then the limit of 1 minus this function also exists because 1 is a constant. Okay, so everything here exists, the limit. So square root of that function also exists. Okay, and then this one, this is a constant function. So limit of x to 0 of 1 is 1. Okay, then you can have a linear property. Cannot. So what do you get? You get a what's the number for this case? 1 minus 1, which is 0. But at the same time, how do you get this 0? You can get it by substitution, which is equals to f0. Okay, so we prove that the limit of that function go to 0 is equals to f evaluate at 0. Okay, or not? Make sense? So, f is continuous at x equals to 0. Okay. So when I do this, when I do this kind of argument, right, I think you need to familiarize now. Actually, I'm checking every point. You see, if you change this number to, let's say, 0.5, it also works. Okay, any number in between -1 and 1, the same thing happens. Okay, so that's why we have this general argument here. Does it make sense? Okay, so whenever I put this general argument, right, you should play around with numbers. Okay, all the numbers in between -1 and 1, it should works. Okay, okay. Right, how about endpoint? Endpoint, we cannot apply similar argument anymore because there's no left right for you to check. For example, if it is a left endpoint, you really can only check the right condition. And for the right endpoint, you only can check the left condition. Okay, whether they are left continuous or right continuous. So similarly here, you should check what is the limit of x go to, for example, 1 minus from the left to the right endpoint. Okay, but this is easily computed as 1, okay, which is f1 as well. And if you go from the right, okay. Wait, yeah, why my iPad is not charging? Okay, so if you go from the okay, so if you go from the right of -1, okay, so what you do here was you put 1 minus of square root 1 minus -1 square. Okay, because the right limit exists for this function, so it's also, you can use substitution. So I mean, okay, there's something happening here, not just substitution. Okay, actually you need to go by limit law. And then this is also equals to 1, which is f of x. Okay. Um, are you satisfying? I think I'm not satisfying. Can I just say like that? I don't think I can say like that. Okay, so let me move a little bit. I think it's better we do like this. So the equal one here is here. This equal here. This one put here. Okay. I don't want to do hack here. I don't think we can just strictly straight away substitution. We should either do either do limit law or we do the whole method, which is by checking. Okay. So this checking could be you draw the table XFX or you already know how to sketch. Okay, actually these two methods is the same. Just a sketch already help you to do all the table at once in the picture. Okay. Any question so far? Any question? Question? Yes. Maybe later. Okay. Oh, you know why I don't want to say you can substitute? Because remember that the substitution we define is just for polynomial function. But now we involve square root. Okay, but how it works for square root? Maybe you need to pass by some limit law. Okay, so that's why I put a limit law here. Okay. Okay, you might need to use limit law to argue. Okay, so I don't want to confuse you, so I maybe put like this. So actually there's something happening here. Okay, so you need limit law. Agree? Don't agree? Agree or not? Do you agree? Maybe you can think about it, okay, and then formulate your question, and then you can ask me again next week. Yeah, or ask on the forum also can. If you are rushed, ask on the forum, the Moodle forum. Okay, when I see it, maybe I can reply or what. Okay. Yeah, think about what I say. Okay. And then maybe you can rewatch the recording again. Okay, so far any question? No? No? Okay. Okay, next theorem, we also have got this kind of linear kind of theorem here. So if f and g are continuous at A, so first condition you have to met is this. Then we could know that a scalar multiplier function is also continuous there. And f plus g is also continuous there. F minus g also continuous there. F times g. F over g provided g of A not zero, so that everything defined. And product of f, yes, multiple times also defined. Square root of n, root of f also fine. Okay, so you can see that this list actually is the same list as the limit law. Why? Because checking continuity is checking limits. Okay, it's checking limits, so limits have to work. The limit have to work, and then continuity will work. Let me recall. Let me call back again. I think the line got problem. Okay. So examples of a continuous function. So now you can add, you can divide, you can multiply, you can scalar multiple, and then take n roots. So these are the continuous function again. So these are the polynomials, rational function, root function, trigo function, inverse trigo, arctangent, arcsine, for example, exponential function, and logarithmic function. These are all continuous functions. And they are continuous at their own domain. Okay. So, for example, how do you know about all the polynomials are continuous? First, you need to prove that y equals to x is continuous. And then from there, you can build all the polynomial x times x, and then times scalar, and add different degree of x together, x with different degree. Okay, so what do we mean by that? So let's look at this example here. Since we know that sine x is defined at x equals to pi, then we will say that limit of x to pi of sine x is really substitution. Okay, because we know that it's continuous there. Okay, so because this is just substitution. Okay, so this is another reason you do substitution. So from here, from this theorem here, do you finally know why we can do the substitution rule for polynomial? From here, do you know that why we can use this substitution property now? What's the reason? Where is it? Here, yeah. What's the reason here? If it is polynomial, then we can do this substitution. Why? After you learn continuity, do you know why we can do this? Because polynomial function is continuous. Yeah. If you look at this equation here, this is the continuity condition, right? Limit of fx when x goes to a to be a. So this continuity problem helps you to evaluate limit. How to evaluate limit? You just by substitute the x and then. So that's why we are interested in this kind of continuous function, because limit is easy to compute. I just substitute my value into the function and got the limit already. I don't need to go and tabulate, sketch. Not it. I just substitute one number. Okay, no? So that's why we are interested in this kind of continuous function. Easy to compute. No need sketch. Okay. All right. Well, let's continue. Again, what are the continuous functions? So maybe you should remember this table. What kind of function is continuous? Okay, maybe you should remember this so that we can straight away use it. So for example, this 3 to the x, right? 3 to the x is also continuous. Okay, but it didn't mention power rules here, huh? Can we apply? So well, we actually can realize 3x to be e to the ln 3 times x actually. Okay. Again disappear. Wait, let me go back again. Okay. Okay. Wait. Okay, I shouldn't talk. Okay. Right. I turned off the speaker already. All right. So if you look at this 3x, right? It doesn't really included in this theorem here. There's no power function here. Do we call this power function? What do we call this? Yeah, so let's recall, what do we call this function? Is it included or not? Let's check. Sometimes I also forget these phrases. So where are the list of function here? These are the exponential function. Okay, good. Exponential function doesn't keep to e. Okay, but every constant b. Okay, where b is greater than 0. All right, then that's good then. Okay, that's good. Hey, do you know why we fix b to be greater than 0? Do you know why? Do you know why? Any idea why we do this? What happened if b is less than 0? What things could go wrong? What things could go wrong if b less than 0? Any idea from here? No idea? Sorry? Yeah. Why we fix b greater than 0? What could this x take? Hey, again, line not good. Should we finish class? You should call up your vice president. Why the line is not good? You know who is your vice president? You don't know. You should know. Huh? No, not country. I mean vice president of this university. Not country. I'm not calling. I'm not going to call presidency here. I mean your university. Wow, this is a bit ridiculous. Okay, so for this x, right, you could take values like half of. What does half b to the half means? It's a square root. So square root cannot take negative value. So that's why this b cannot be negative. Okay, always it's positive. Okay or not? Okay. Okay. So in this case here, we are good. So we know that it is continuous at any place it defined. So since 3 to the x is defined at x equals to 4, so by the theorem above, we can just substitute 4 into x to get the limit. So 3 to the 4 is what? 81. Okay, just 81. Okay, so maybe one thing you should remember out of these 3 hours is if you have a continuous function, if you want to compute limit, just substitute that point into your function. Okay, if it is continuous, just substitute. The point is you have to know it's continuous. I cannot simply substitute. Otherwise, you get wrong answer. Okay, next one. So composite limit theorem. So if you know the limit of gx, and then you know that f is continuous at that point, then you can compute the limit of the composite function. Okay, so how to compute? Well, what you can see here is you can commute your limit with your function. Okay, and then you just evaluate f at the limit of g. That's it. Okay, very convenient here. Okay, this is very convenient. So let me show you one examples here, how we do this. Not that. This hash x here, we can realize at the composite of two functions. Okay, so what are the two functions? What do you think? What's the f could be? What's the g could be? Hmm? You could do x squared minus 3x minus 6 first, and then only you do the absolute value. Okay, so these are the two functions you can see that I can split it up. So in function, right, there are two ways to split function up. I mean, more than two ways, but one way is product. The other way is composite. Okay? So composite, you can understand it as I want to do gx first and then do f. So meaning I do the quadratic function first, only I take the absolute value. Okay, okay. Can I swap the order? Can I swap the order? Can I do f first and then do g? You remember or not what I drew just now? F is absolute, G is quadratic. If I do F first, I do G, what happened? Everything inside, every variable inside the quadratic become absolute value. So it's a different function already. Okay, it's a different function already. I need to reconnect. Okay, right. So in this case here, how do we use this composite limit function? What is the condition you need to check? You need to check limit of gx. Does it exist or not? Is it equal to something? Can you quickly see, does it exist? Limit of gx. We want to check where? At every real number, every number, does it exist or not? Because gx is a polynomial function. So polynomial function is defined everywhere. And then so it's continuous at everywhere. Okay, so can we write it down? So first, gx is continuous at every real number as it is a polynomial function. Okay. So then we need to check whether fx is continuous at all these points or not. Okay. But absolute value function doesn't lie into any of these category, right? Is absolute value function lies in any of this category? No. We didn't talk about piecewise function here, huh? Okay. But we know that this piecewise function here is built by what? It's actually built by two polynomial function. Okay, if you still remember. So to see that f is continuous at every real number. Okay, let's write down the definition first. So by definition of f, what is it? You send x to x when x is greater than or equal to 0 and minus x when x is less than 0. Okay. All right. So since f is just polynomial at these two regions, so this region is minus infinity to 0 and 0 to infinity, then we will say that it is continuous there. Okay, because it is just polynomial. So the point you really need to check is where they connect. Where are they connecting? They're connecting at x equals to 0. Okay, but I think we compute this a few times already, right? So left limit of absolute value is what? 0. Right limit is 0. At that point, you use the first definition or second definition to check first. So f of 0 is 0. Okay, so let's write down. So I will just quickly write here by calculation before limit of x to 0 of absolute x is equals to f equals 0, which is f of 0. Or if I want to write it properly, it's absolute 0, which is f of 0. Okay, so so f is also continuous at s equals to 0. Okay, hence f also continuous at every real number. Okay, so we can use composite limit theorem to say that hash is actually equals to f compose G, okay, which is continuous at every real number. Okay, any questions so far? Question from here? Question? Understand? Any question? Here, understand? Here, back? Question? Feel free to ask. On the right, a question? Okay, so if you don't have question, I'll try and apply my technique to these two questions. Okay, I will leave it as a homework. Then we can either check solution next week or I just post out the solution and then see you get the same answer. Okay. So I think we're a bit behind of the schedule. Hopefully we can pick up, finish chapter 2 by next Wednesday. Okay. And then we'll start the derivative. All right. Have a good weekend. See you next week. Yeah.